In this lecture, we will first consider a case study of how data analytics applied to real-world problem. That is, we will consider to build an email inspector that can automatically detect spam emails. Before we can apply any analytics techniques to the email data, we need first to represent the very flexible form of emails into some more manageable and mathematically more operational form. So we first discussed data representation for text, which is not only applied to email messages but also to other data in text form. In this lecture, we employ decision trees as our classifiers to detect spam emails. Decision trees mimics the natural procedure of making decisions based on asking and answering a series of questions related to the information available. We will first look at how decision tree works. That is very intuitive, and we will consider how to build decision trees from observed data. Then we look at this family of classifiers from the perspective of learning framework and how it related to and differs from the classifiers we discussed previously, namely those parametric, that means the model employs weights, parametric classifiers like perceptron and neural network. Lastly, we will consider decision trees and the rules of building decision trees from information theoretical point of view. So let us first look at the data. For example, if an email looks like this, from a glance, I think one can tell that there shouldn't be much information to get from this message. So that is, if you ask me, I call that a spam. This one, look at the grid price. It is spam as well. And this image, that looks more genuine. The problem is, of course, how to generalize and formalize this intuition-based rule of determining whether a message is a spam or not. We have considered models that has parameters as width, and when you use those widths to adjust the importance of different attributes, or we can call them features of the data. For example, if the data has two features, x1 and x2, we can give them width w1, w2. One can sum over those weighted. We can have this. One can have this weighted sum of the features, and use this weighted sum to determine if a message is if the data, whether or which class the data sample should belong to. But given an email, the first problem is where are those attributes or features on which you can apply or associate with your weights. To have a clearer aim of representing the text or email data, let us first review the more regular data we have encountered so far on which those weighted model can be applied. Those data are often come as a matrix, which is just a two-dimensional array of numbers. For example, we can use one dimension like the rows for the data samples, and the other dimension for the attributes. Each row of the data matrix then represents some real-world entity or an object. In this case, in our example, is an email message, and for Each of the object, it is described by a certain number of numerical attributes. That is the numbers in that row of the matrix. There is one notice we may want to take for the data matrix. Mathematically, the matrix has two dimensions, and these two dimensions are symmetrical. That means if you rotate a matrix by 90 degrees, making the rows columns and the columns rows, we will arrive at another matrix that is there is no significant preference for one matrix over the other, because the rows and columns has similar meanings. However, in data analytics, we often distinguish between the rows and the columns. It doesn't matter which meaning you give to the rows and which you give to the columns, but the two dimensions are generally considered different. The difference is that the dimension associated with the entities. In our example, that is the row dimension. In this dimension, we normally think the data are independent. One row is independent with another. But for the numbers within the numbers associated with one entity, that means the numbers in one row of the matrix, they are often considered to be related to each other. Think about an example. If the rows represent people and for each people we only consider two attributes, that is the height and the weight. Generally, knowing the height of one people would not give you much information about the height of an unrelated person. However, knowing the height of someone will generally allows you to have some educated guess about his or her weight. So the columns are correlated and the rows are independent. That is the basic assumption of the simple data matrix. So a regular data matrix is really a very convenient way of represent the observations. Now let's come back to our case of analyzing text. And text data is obviously more flexible, and we need to find some way to fit the information in text bodies into the regular data matrix. So many of the data analytics model can work with text. Text is ubiquitous in many fields, used in government, in industry, business, academic. The data may in the form of newsreels, research publications, books, and some business documents, and in today's example as email messages. Of course, it can be online as web pages, and text data is continuously generated in huge volume on online social media such as Twitter and Facebook. Often, text data has some semi-structures in it. For example, if the records are research papers, often we know where is the title, who wrote the paper, and on which forum or journal the paper was published. But some of the fields are more flexible, such as the abstract or the body of a paper may take arbitrary text forms and make the information in it more difficult to extract. Here is a concrete example of the text data. In today's case study, we will consider how to analyze email data. Those emails are stored in folder structure on my computer, and if you download the data in our course website, you can unpack them in a folder structure. The messages are organized into those directories, and in each directory, each email is stored in a single text, a plain text file. In the training data, spam and genuine email messages are organized in different folders. Of course, in the test stage, the message comes with the same subfolder structure but without being given the ham or spam tag of the messages. It is obvious that given those text files, it is very difficult to directly apply those data models we have discussed, or in this sense, to invent any data models that can be directly applied to those text models. However, as we have seen earlier, we can have some intuitive way to distinguish spam messages from genuine ones by glancing at these messages. So let's first consider how those simple intuitive rules are constructed, and from these rules, we may find some inspiration on how to deal with text data, represent them in a regular form, and design models to classify those data. Examining a message, we may look at its title and the first few lines of the message. And for me, I'm scanning the message for keywords. For example, money as a word is normally does not imply good, imply well that the message contains useful information. If in a few sentences I find free this and free that multiple times, more likely than not the message is a spam. And if this isn't the case, we may continue this inspection further down. Key point here is that the task is not to invent a set of rules to distinguish each email message individually, but to design the mechanism that we can program into a computer and let the computer automatically classify those messages. So to have a prescribed set of rules, we need a fixed set of keywords from which the rules can scan the message for each of the keyword from that, let's call it vocabulary. And for each of the keyword in the vocabulary, we can count the number of times this keyword appears in the document. Recording this series of numbers, and then a document is represented by a fixed number of numbers, a number of word contents. In this way, regardless the length of the document, it will be represented by a fixed length vector, and in the element of the vector are word contents, because we are using the same vocabulary for all those documents. And put the word counting vector of all the documents together, we will arrive a regular data matrix. More formally, the preprocessing of text data consists of 3 stages. The first one is what we just discussed, to count the word appearance in the document, and we need also to further optional processing steps we will discuss later. So in technology terms, they are tokenization, remove stoppwords, and steaming. Tokenization is just a fancy word to find the unique words in the documents. Actually, not only words. By words, here we mean token, and a token is an atomic unit of meaningful expression in a language. For example, the word hello conveys a small piece of information in the English language and can be taken as a token. But generally, we will not consider a single letter, for example, that H in the hello as a token because it is normally not meaningful. Sometimes a token consists of more than one word, such as United States. And these two words combined together point to one atomic meaning in the language and is considered as one token. But in a basic preprocessing, we can just think English words are tokens. That is acceptable. And the second stage is optional. We can remove the stop words. Some words are so commonly used in the language that they do not, and most often, in most cases, they do not convey any meaning, like the, of, and is a stop word, and some other words depending the context of the application. For example, if you if you try to analyze document in our course, website, the name of our university may not be very meaningful because almost every document contains that name. And there is another step called steaming. After we have all the tokens in all the collections of the documents, we may think that some of the tokens are so close with each other that they should be taken as one. Examples include the different tenses of verbs such as get, got, take, took. Mostly they mean the same thing, but are used in different occasions. And for nouns, the single and plural forms of nouns often means the same thing, such as computer and computers. If you consider them literally, they are two tokens, but for more efficient processing, we can cluster those tokens into one. After these three steps, we can convert a set of documents into a data matrix. In each of the rows, there is one document, and the numbers in the row represent the counting of individual tokens appearing in that document. Having the principles of the preprocessing steps and preparing text data, if one wants to implement them, there are many technical details need to be considered. However, fortunately, those subtleties has been taken care of. We can employ very effective language processing packages to prepare text data for us. And in today's demonstration, we'll employ the function called count vectorizer. That means to vectorize or prepare a document into word counts in the scikit-learn package to help us to prepare those email messages. And here is an example of how the vectorizer works. Let's give it a set of documents. Each document is of course very simple. In this case, we give it 3 documents, and each document is just a string, that is a sentence. Like we give it hello world, and like these three sentences, and say that it can convert these sentences into these 3 vectors. And the vocabulary is listed down here. If you look at it carefully, in the first sentence is hello, comma, space, word, exclamation. and the comma and the exclamation are excluded from the tokens, and only hello and word are taken account for, and all letters are converted into lower letters. Let's find where is the hello in the vocabulary. That is the 1, 2, 3. The fourth word is hello. And have a look at the fourth number in the first row of the matrix. That is 1. So this sentence contains one hello, and go all the way down. The last word contains one word. Okay. Have a look at the last sentence. The last sentence contains, look, 1, 2, 3, 4, 5, 6, the sixth token, that is not. Okay, it contains the not once, okay, and or once, and program twice. Okay, to program or not to program. There is two programs, and there are two tools in this sentence. So hopefully this clarifies how the word counting representation of a document works. After counting the words or tokens in a document, one may want to some further processing steps to make the data more informative and representative of the target value, and that is the information we are really interested in, more obvious. For example, if we count a very long document, there may be many appearances of those terms or tokens or words. And if we count a short document, the count of those words may be less than those counts in the long document. However, the subject of a document may not be directly related to the meaningful aspect of that document. By meaningful, we may say the mood of the author. Is the author try to convey a sad or a happy message, or which normally we call that sentient analysis, or the quality of the message. Is it a good composed message, or a very carelessly prepared one, or the topic of the message? For those what we call more meaningful aspects, this may not directly related to the length of the document, and therefore not to the word counting descriptor of the message. Note that by describing this problem, I do not suggest that the long document has long word counting vectors and the short ones have short vectors. The word counting vectors for all messages are the same, but the elements in those vectors can be great or small depending on the length of the document. So a natural idea is to take some normalization of the messages. For example, we can divide the word counting by the total number of words in a document. By this normalization, we can have two word counting vectors of two documents more or less within the same order of magnitude, and they are more comparable to each other with respect to those more meaningful aspects we just discussed. In fact, there are multiple ways to normalize the word counting into more what we can call that meaningful form of descriptors of document. For example, to eliminate the absolute value of the word count, we can convert the word counting into a binary counting. That means we only the presence or not of a word or a token in a document that really counts. And any non-zero value is converted to 1, otherwise it remains 0. And of course, we can use the original word counting matrix, and we can also do the normalization we have just discussed. In technological terms, that we call them term frequency. We call the result of this step of processing as a term frequency matrix. On the other hand, another intuition is that if consider two types of words. One is common words. Some words are so common that we call them stop words, like of and the. We do not include them because they are so common and doesn't give us much information. But some words are not so common, but also common, like the word of university or computer. If a word is very common, we think when it appears, its appearance conveys less information than some rare word comes, like the tokenization. You rarely encounter that word in everyday life, and when a document contains that word, you have a very good confidence that that document is more likely to connect with natural language processing, this topic. Okay, now these types of features is called inverse document frequency. It's calculated like the total number of documents divided by the number of document contains the term. Okay, normally we can combine these two terms together. It's called term frequency, inverse document frequency features of a document. This is the element by element multiplication of two matrices, and the result is a matrix of the same size as, of course, TF matrix. Now we have the regular normalized matrix representation of text data.